essentially all the time unless my machine breaks down. Why would I want to measure it every fifth part?
Well, because you can set it to the lower and save steel costs by really aiming at the lower edge if you're really capable and avoid investments in materials.
That would be true. That's another good point. So we have our process spread. I'm actually working on a problem like that with one of our suppliers of how do we nestle up against one edge of that. And it's a very subtle thing. We're going to talk about the difference between process capability and then this K is whether that process is centered on that. But the biggest thing I want you to get from this is that if you don't know how much variation relative to your specification limits are, how do you know how frequently you're going to need to check the parts? Okay, so that's the aspect of the process. Any comments related to process capability?
Yeah, just our lack of understanding this means we throw more waste inside the process. We throw extra stuff in there because we don't know what to predict.
Well, it can, my point in some of the things I've worked with is we have suppliers who are measuring every fifth part, even though their process is ridiculously capable for the specification. And so I'm encouraging them to look at the specification relative to their process. And the reason that's important to me is I'm going to suggest to some of them that they actually drop some of their inspection frequency because it's more likely going back to controls. I'd rather have like a metal fabrication company that has a CNC X and Y movement. I'd rather have them cut one sample part like once a week and measure how precisely circular that donut is that's cut out of that. Because the control axis or the servo motors is going to determine more of what the process capability is than these control planes. So that's going back to Jeff's comment of that. And I don't know if we've done much with metal suppliers in regards to that, but frequently in metal fab, 5 pieces, 10 pieces, everybody measures them that frequently, even though very few people actually compare that to the spread of the tolerance.
So on the control plan, Jared, you're saying you want to check the process capability. What we do in our industry is we do that independent of, we do a process verification and validation, an IQ, OQ, PQ, independent of production and the control plan. So we do that prior to developing the control plan.
So if I can state that another way, that you know your variability of your process prior to overlaying the requirements for that.
Yeah.
Which is great because, as I said before, there are some suppliers I deal with that there's kind of like this, they get the glossy brochure for the piece of equipment they bought, and then that's what they call their capability.
Yeah.
And they've never actually measured it. And especially with machine tools like mills and things with servos, it's how old the piece of equipment is. It's not
Aware.
who made it.
Exactly.
Or maintenance can make a huge impact.
The other thing we do up front of the control plan is we also do our MSA on the equipment we know we're going to be using to measure and monitor our process capabilities.
Good lead in. So what is measurement systems analysis?
It-
Because we're going to cover that next week, but what is a way to describe that?
Gauge R&Rs, looking at your calibration of the equipment, making sure the equipment you're using to verify your process and verify your product are capable of measuring to the tolerance specified by your customer. It's the system to manage that.
I want to try throwing another more loosely defined way of looking at it is how much of the variation is due to the measurement tool I'm using.
Yep.
So if I'm using a, if I'm using this to measure my location of the, is this coarse enough, Jeff? Like if I'm, would you like me to use this to mark out the holes on the the PCB router?
No.
No problem.
Why? You don't think this would be a,
It's not.
It's a
not
pretty
got
tool.
The intricate detail, the resolution that I need.
okay. Even if I have my eyes calibrated to that.
No.
If you have them certified.
Sometimes my wife thinks I'm certified.
Guess who's doing the game on R in the eye? Brian.
So the point to this is that when you're using your control plane, you need to know how consistent your measurement tool is to measuring that specification. And so this is another place where companies that are not mature in quality practices, they go, well, I have a, I've even had some suppliers tell me, well, I have a calibrated tape measure. Is what they call it. It's a true, it's a calibrated tape measure. But the problem is we're measuring to,
Thousands.
maybe not thousands, but
10,000s.
the most frustrating thing with that calibrated tape measure is that we actually went and looked at it, and they were using English units with fractions, and we're calling out on our drawings decimals. So, how many typical machine operators do you know that are going to go figure out what the fractional equivalent of a decimal is?
Every one of Ben's. Right, Ben?
He hasn't answered yet, so. All right, so sometimes these things are best done by practicing them. What I'm going to do here is I'm going to give you a formula of how to estimate, let me back up, I haven't explained this measurement system very well. So the book gives us some examples here. We're going to do the MSA next week, but this is a rough description of what I've told you, that if 10% of the variation is due to the measurement tool, that's can be acceptable as a starting point. 10 to 30, depending on the application, might be acceptable. Anything greater than 30 is, that is just, what do we draw a circle, put a line through it, that's just not going to happen. Or it can happen, but it should not happen. Does that kind of make sense? So when we say 10%, one way to do that is you make a measurement. If you're making the same measurement each time, 10% of that variation can be explained by the measurement tool that you're using, or method, or the measurement system, which is the tool and the fixturing, etc. for that. Operator.
So I gotta make sure I understood it, Jerry. So I have a tool I'm using to measure and build a product, and using this tool, I get failures. And so if 10% of the failures, 10% or less are false fails, then that's good, acceptable.
No, that's not what we're saying. That if I use a measurement tool, and I'm going to have a observation that is not absolute, is that a way to describe that? For some imaginary number that is the real number, because there's always measurement errors, so you can never get that perfectly. But,
Just measurement error.
we're saying here that if your device or method of how you're measuring that, if you have 10% of your measurement can be explained by just which tool I'm using.
May I?
Yes, go ahead.
I was working today earlier with our receiving group,
And me.
explaining, and Jeff, on gauge R&Rs, and we went through this. Would you mind if I draw
ahead.
kind of on the board?
You can do that fairly
At my direction.
Yeah, in Gerard's direction.
I gotta leave it.
So,
Who's the guy?
yeah, Gerard's gonna yell at me for this, it's all wrong. But whenever you're making a measurement, you have three
Who's got
sources of
my
variation.
scorecard? Right, did you finish it?
I
Yeah.
told you he wanted the scorecard.
Because it's focus, man, I'm telling you.
I'll
Okay, you got my number? Call me tomorrow. Give me a-
I'll look at with him.
Yeah, because I'm gonna, yeah. Just kidding.
So Brian, if I may say, you're looking at the measurement system. Some people talk about the equipment, which is the variation of what the tool you have, right?
Right. So if you're taking a measurement, so I'm a receiving inspector, and I'm told that I'm supposed to measure this part, and it's supposed to be a certain length. All right, and it has some sort of tolerance on it, but that's what I'm told to measure. Well, I decide that I'm going to use this to measure it, and it's got some sort of scale on it. So I will go in and I'll take measurements. So I may take measurements, and when I make measurements, I'm going to have some sort of error, and it's going to be X%. I give it to anyone here, and you guys make a measurement, and you're going to have not necessarily the same variation I had. I measured this one, that one, and another one, and I got different values for all of them. That's appraiser variation. That's within me. I'm not that accurate. You may have a different answer, and if you're getting the exact same things as me, you're saying that you measured the exact same value as me, so the equipment isn't changing, or sorry, the appraisers, if you measure the same thing as me, you are saying that there's no appraiser variation because you get the same answers. But if you get a different answer than me, you're saying that here, there's another form of variation. And so if we all measured exactly the same thing for all of them, all the variation is from part.
That
What-
was, the parts were different sizes, and that's why we got different answers.
Right. So when you're saying that for your MSA, your equipment has to be capable, when you take X% plus Y% for people measuring, and you divide by the, as a fraction of the total, this has to be less than 10% of your variation when you add them together. Because if it's more, you're saying that whatever you're using to measure or going from person to person using this tool, you can't reliably measure part variation because it's not accurate. Does that make sense?
Any differences in measurement we get of the same part should be because the parts were different sizes
Mhm.
and not because the gauge or our ability to use it consistently are causing the difference.
So another reason this is important is that it is possible you may say that a part is not in specification when it is.
Mm-hmm.
And then there's also the other risk of, whatever the opposite is, I always forget. Does that make sense? So,
Either way.
Should be, right.
so that is why before you can do a control plan, you need to have some, at least, intuitive understanding of that variation.
How do you calculate the X% on appraiser variation?
Give them the formula, Brian.
If you'd like, I can bring in the formulas, the charts that do this. We
Yep,
can
so-
run through examples for next week.
It's in the next chapter. There's roughly, I don't know, maybe 5 different industry-accepted ways of doing that. You can either do it through ANOVA, like if you guys have Minitab.
Well, what I'm trying to understand is what that X% is telling me. So that's why I was wondering.
This is the
if I knew how
variation
you
between
calculate it,
appraisers.
I know what
So
it's telling me.
if Brian and I measure the same thing, how much of the variation can be explained by the difference in the way he and I do it?
So I measure 1, he measures 1, and he measures 1 on a unit. We've all measured exactly the same thing. The next unit we measure, I measure 1.1, and so does everyone else. 1.1, 1.1. If you take the amount of variation here, there's no variation between what I'm measuring and what he's measuring. And there's no variation when we measure between parts for what we're measuring. All right? So say now that's my first study. So that's the first time we measure. We go back in and we do the same. So this is a separate one. And we go and measure the same parts again to see if I'm varying when I measure. And I measure 1, 1, 1, and he measures 1, 1.1, 1.1, 1.1. All the variation here from me to him is appraiser variation. The total variation that you calculate would be 100% X. None of it is part equipment variation. We use the same equipment, we got the same results every time. We both measured the same thing every time we measured the part. So the equipment's on, and there's no variation in between the parts we're measuring because we always measured the same thing whenever we measured any given part. Does that make sense? And so say you change and say, I always measure, I'm going to just change quick going through, and say that we both measure 1.11 on all of these. So now you're going to say, as we went through, between the time that we measured, actually to make sure that this is actually absolutely right going through, if this is a 1.13, now we measured the same thing every time again. This time, we didn't have any appraiser variation, we measured the same thing. But our equipment between the first time that we measured, the second time that we measured, and the third time that we measured changed. So all our variation becomes equipment. And then this one would go back to 0. And then the equation's the math behind it. It's easy to see if you're doing one value. You can see it's all either appraiser or all equipment variation. But say I start mixing values, and this one becomes 0.2, and I can't do this math in my head, but now you're saying some of this has an appraiser variation and some of it has equipment variation. And when you run that through the equations, it'll give you the percentages. Say, I'm going to give a rough estimate here that's going to be not quite right, but I have 12 data points. One of the data points is off for appraiser variation. The rest were off for equipment variation. So this is going to be somewhere around, I'm going to go to fractions instead of percent, but 11/12. And this will be somewhere around 1/12. Okay. Right?
So Brian went a step further. We're just looking at the measurement system, which can be appraiser, equipment, experience. We can go into a whole bunch of other ones with that. So we're just going to lump all these in and just say how much of the variation is due to the part and how much is due to our measurement system. This is as an aside, but it's interesting that in the MSA literature, there's even doing visual inspections of like color. You can find out how closely your measurement system, which is a judgment call on a Larson door, is this really white or is this other white? Which I'm sure that every company that's had paint has that conversation of people standing out there trying to decide, is that real white,
We actually have
off-white?
a meter for that, but.
Last Thursday.
Yeah.
But you can do the same type of experiment by giving paint chips to different inspectors or people and find out how much of the variation is due to the, and compare that to a actual measurement device you probably have at your lab.
Yeah.
Yeah. But then you want to make sure they all have the same measuring device, or you still get variance.
Right, but it's interesting to see that the literature wasn't just about using calipers, it was judgments. And I thought that was interesting to include, because that's the most difficult thing I think in manufacturing are those things that are more perception. Like we at Daktronics have contrast is a big deal on our displays because we want the LEDs shaded and hidden from the direct sunlight. And so we have a difficult time of getting, there's cases where we have numerical values from observed calibrated measures of black. They're both flat black, but they look different to the human eye. And so you can imagine you deal with the same thing on a door. Is it direct sunlight? Is it, you know? So anyway, that's getting aside. So we've established that we want to make some type of estimate of our measurement systems analysis. And that's not necessarily going to directly go into a formula, but it helps us appreciate how frequently and the size of our samples we need to take to discern if there's a shift that's taken place in our process. All right, CPK, what I'm going to do is write a formula up for you guys. I'm going to look up here in a moment. Unless someone, you want to know that off the top of their head, you can recite that. That one where it's, is that the right one, or is it, it's the max? Did I get that right, or is that, no, this is 3 sigma, isn't it? Anybody remember that off the top of your head of CPK?
It's 3 sigma. I
That's 3
believe.
sigma? Did I get the rest of this right?
It's right except for possibly, I don't remember which one comes first, from LSL or USL.
Well, we know this is gonna be smaller than what our central
Good.
tendency is gonna be. So that would keep us positive values. All right, so rather than worry too much about this formula, a CPK, let's just use the phrase small, medium, and large. Let's just call it that. So let me draw 2 pictures for you, 3 pictures actually. Because it's really not fair to expect formulas out of people that haven't even had time to really look at that. All right, this is the typical, we'll call this medium. Right, so this is counterintuitive almost, that a tight distribution has a large CPK, which is desirable, and a wide process spread relative to the specification has a low process capability. So, if you have a low CPK, in other words, your variation of your process is wider than what your specification is, that means you should have a higher frequency of checking things. If you have a very tight process that can wiggle a lot inside the specifications without going outside the specifications, then you don't really need to check that quite as frequently. So what I'd like to do over the next, probably more than 15 minutes, but let's say less than 30, I would like, you can be in groups of 3 or less people, and I would like you to have 6 different processes, and I'd like you to attempt to fill out a chart on this, and if you have questions, as you likely will, please ask me about how to fill that out. Does that make sense? So try to do it with a product or process that you're familiar with, so that you can maybe intuitively fill out this chart. So from the academic side, no more than 3 students. You can have more factory people with you if you like, industry people, but only 3 students per sheet that's turned in today. Okay. Any questions before you get started? Yeah, so I want at least 6.